Hello, in this video it will be shown how System Tuner Studio can be used to design DC-DC converters. System Tuner Studio, STS, is a tool designed to optimize the performance of any system, electronic, mechanical, optical etc., as long as it can be described analytically. Since the programming is carried out using C#, there are no limitations on the complexity of the system. A library of functions speeds up system programming. In this video, the performance of a previously programmed system will be shown. The details of the programming are explained in video D105. As an example, we will use a simple buck converter, but the method can be applied to any converter. This is a buck converter which is fed back with a proportional integral, PI, type compensator, which converts 10 DC volts into 6 DC volts. All the components used, specifically the operational amplifiers, are ideal, so its purpose is exclusively educational. At the end of the video, the proportional integral compensator will be replaced by a proportional integral derivative 1. This is the plant circuit. And this is its transfer function. This is the compensator circuit. And this is its transfer function. In this way, according to the control theory, the closed-loop transfer function should be calculated this way. And this is the formula for the open-loop transfer function. These functions are all you need to edit the system, the buck, in this case. If the input voltage, 10 volts, is abruptly increased to 14 volts, the 6-volt output voltage will be transiently disturbed. This converter is stable but can be optimized according to different criteria, for example by decreasing the settling time. The parameters to modify will be the constants Kp and key, that determine the compensator behavior. STS is made up of 3 fundamental cores: the system editor, the figure of merit editor, where it is programmed how the system is optimized, and the tuner, which is where the system is actually designed. As said before, another video will be devoted to explaining programming, so we're going to jump right into the third core. There are several ways to open the tuner. This button is to create the project starting from the previous written code. This button opens an already created project by searching the Windows Active Directory. This one takes us to the project library. This one allows to select the project among the most recently opened. And this one directly opens the last created project. If this checkbox is not checked, the Bidimensional Tuner opens. But if it is checked, the Multidimensional Tuner opens. So, let's open the last project, which is precisely the example at hand. The main controls of the two-dimensional tuner are the following. This one allows access to a description of the system. Through this one you can see the system programming. This one contains the parameters of the system, and through it, it is possible to change its values. This control allows you to view the figure of merit programming. Perhaps the most important is the optimization control. To each point of this square corresponds a value of Kp and another of key, and what is involved is finding the point, or the region, for which the system behaves in the best possible way. In this example, the best behavior is associated with the shortest settling time. The red areas are the worst and the green ones are the best. The dark green regions correspond to forbidden zones given the constraints that can be imposed on the system variables. In a few seconds you will see how this works. This vertical bar graphically represents the figure of merit value. This other graph shows the transient at the converter output and the settling time, which is bounded by the blue region. Finally, in the output data window, the numerical values of various parameters are shown, such as the settling time, the position of the poles, the crossover frequency, etc. It can be seen how when we go towards the red zone the system stops being stable and when we go to the green zone it stabilizes. Within the green zone there are some zones better than others. The idea, as mentioned above, is to find the zone with the highest figure of merit, which will determine the values of the compensator components that result in the lowest settling time. To do this, the tuner is activated by clicking on the Tune button and we see how the settling time is significantly reduced. The two-dimensional tuner dynamically displays other commonly used graphs, such as Bode plots, the Nyquist plot, the position of the poles, and in general any graph that the system programmer wants to display. Let's start with the poles. At this moment, the three poles are in the left half plane of the complex plane, which, as is known, corresponds to a stable system. If we move in this direction, there comes a time when the P0 pole is located to the left of the other two poles, they change from blue to yellow on the graph. In the first case, blue poles, the transient voltage values are always greater than the 6-volt stabilized voltage. But in the second case, yellow poles, the transient oscillates on both sides of that voltage. If we continue moving towards the red zone, it is seen that the poles P1 and P2 pass to the right half plane, with which the system becomes unstable. On the other hand, it is also possible to activate the rest of the additional graphics. The Nyquist plot, and the Bode plots. Let's create an automatic sweep in the optimization control. Now, let us replace the proportional integral compensator in which two adjustment variables, Kp and Ki, are used, by a proportional integral derivative one, where it will be necessary to add another adjustment variable. If the capacitor C1 is added to the Pi compensator, it becomes a PID compensator, whose transfer function is the same as that of the Pi compensator plus the term Kd times S. This is the multidimensional tuner, where the values of the components are the same as those used in the previous case, and since the value of Kd is 0, we have the same transient as before. We now define the variation ranges that we are going to allow for Kp, key and Kd, and we start a first optimization taking into account only Kp and key. It can be seen that something similar to two-dimensional optimization is obtained. We now include KD in the optimization and see how the settling time is reduced even more. With the multidimensional tuner, you can study the influence of each of the parameters. Let's go to the starting point. We see how the parameter KD influences the transient. Same for key. Also for Kp. This is also valid for the rest of the parameters of the converter, such as, for example, the value of the plant resistance. Additional functions that are available for the two-dimensional tuner are also available for the multidimensional tuner. You can take advantage of System Tuner Studio in different ways. You can develop projects of your specialty for your own use or for your company. You only need very rudimentary programming skills and writing a few lines of code. But you can also develop libraries of projects associated with a certain theme and market them. The source code of the algorithms you develop may optionally be protected. End users of these libraries do not need to program anything, they will only have to modify the value of some variables to adapt the project to their particular case. The Sofnius team, the company that developed System Tuner Studio, is ready to help you with your goals. Sofnius team will appreciate your comments. Thank you for your time.